Okay, welcome back to the second part of our calculating different types of velocities for Maxwell-Boltzmann distribution. So we did the V most probable and V average. So right now we want to do, actually this is the most difficult one, V root mean square velocity. So what's root mean square? You take the square of all the velocities and find the average of that, or the mean, and then you take the square root of it. So to do this, first you have to actually uh, use this integration. And it's a little bit difficult. So what we want to do is that we want to step back first and introduce some of the techniques that will be used to solve this integration. So one of the techniques is that, so what I would call it, you have an exponential function. So how to integrate exponential functions and some useful techniques. That's what we will call this, some useful techniques. So the first thing that I want to do is, let me use a blue pen for it. What I want to use, if I simply take an exponential function e to the power minus alpha x, or even plus x, right? It doesn't matter. Let's say that if I just do an e to the power alpha x, I get alpha e to the power alpha x, right? If I take the integration of it, e to the power, for example, minus alpha x, what do I get is that minus 1 over alpha e to the power minus alpha x, go from 0 to infinity. And the answer, the the first one is 0, and the second one would be just plus 1. So it is 1 over alpha, right? Keep this in mind. Keep this in mind. This will be helpful. So what we want to do is we're going to introduce this integration as a function of a, and I'm going from minus infinity to plus infinity, e to the power minus alpha x squared, let's say dx, all right? And I don't know how to do this one, for example. That's in here, by the way. That's in here, in the Boltzmann distribution function, right? What I can do is I'm going to multiply the same integration with itself, all right? So what I can do is that I can say, you know what, the integration, and this integration, I'm going to do minus infinity to plus infinity, e to the power minus alpha x squared dx, e to the power minus alpha y squared dy. As you know, these are just variables, and in the end, when you put the limits, it doesn't matter whether it's x or y. Basically, this and that integration, they're the same, right? They will give the same result. So this will give me I squared a. All right, so let me expand this one right now. So I can write this out as minus infinity. There are two variables here. Each one of them is going from minus infinity to plus infinity, e to the power minus, and I can add these two guys. They're in power, right? And then I have dx, dy. Those are my two variables in x and y. Okay. Then I want to move over to polar coordinates, which again is a technique. You can go from a Cartesian system dx to dy to a polar coordinate, and basically what my polar coordinate is that you have an r, and then you have an angle, could be theta, could be phi, so whatever x and y is, for every x and y point, I can move it over to an r and phi point, right? I can determine if there's a point here, it's 10 meter in x, maybe 9 meter in y. I can make it over here, maybe about, I don't know, 11 or 12 meters, and then I have an angle which would be 30 degrees, 20 degrees, whatever it is. So I can move over from one coordinate system to another one. So when I do this, my x squared plus y squared becomes that r squared. Remember, this is how I'm writing my r. And then dx dy, this basically your area, dx dy, it becomes dr d phi. Okay? And I can, so this is very crucial right now. I hope we can see it. This is I square a, because I times I square. It actually, now going from infinity to infinity, minus infinity to infinity, becomes 0 to 2 pi d phi, because, you know, we're looking at the plane which encompasses everything. So you go from 0 to 2 pi right there. And then your r goes from 0 to infinity forever, right? R dr e to the power minus alpha r squared. Okay? So what are we doing here is that, so you're going from dx di to, this would be, beg your pardon, this would be r dr, right? R dr. And make sure that you, I'm not going to go through this, you know, this system, that why you can do this Jacobian. I'm assuming that you know that that's how the conversion happens. Okay, just a little bit of hint that I can give is that if you look at a particular dr, why that, so for example, I'm looking at this area right here. Okay, so this is your r, so that thing is your r, this is your d phi, this right here, so your dr would be this area, this is your dr, and this right here would be r d phi. So if I'm going to make an area here, and this area is that arc right there would be r times d phi. You're looking at a very small angle, and then this, your dr would be the width. So r d phi times dr basically is your area. Okay, you convert it that way. All right, so we just moved over to the polar coordinate system, and what's my next step? I need to evaluate this integration. So what I can do is that I can write, take u to be r square, you convert that u r square, and du would be 2r dr, and you can see why we did this r dr. You can write it as du. Okay, so then I square equals to, I'm writing over here, let's say this d phi, it becomes your 2 pi, so that nothing changes here, 2 pi. And then you go from 0 to infinity, 0 to infinity, you have e to the power minus alpha u du, but there is a 2 comes underneath, so there will be 2 over here. Okay, and what do you get here? Well, remember, we already know how to solve this integration, right? And that integration would be simply 1 over alpha, right? So this guy is simply with 1 over alpha. So in the end, you get, what you get is pi over alpha. Okay, this is great. This is the only thing I need to actually figure out. So what's my answer? My answer now is if it is a part of alpha. Did I change it to a to alpha? Okay. So anyway, it's the same thing, a or alpha. So this one would be simply root pi over alpha. Okay. So what's root pi over alpha? This is our integration, minus infinity to infinity, e to the power minus alpha x squared dx. That is, this integration is root pi over alpha. Now you know, I mean, irrespective of whether you're solving for molecular distribution speed or not, that is your integration. That's one way of solving it. All right. So let me just talk about a little. We're talking about kinetic theory of gases. So some more useful integration, how we do this. So more techniques. So there are some more techniques that in future we'll be able to use. So one of the techniques would be, if I take that guy and I just differentiate it from minus infinity to plus infinity, just take it, okay? So you can notice that I'm differentiating with respect to alpha. I'm not touching x at all. And actually, if I do this, what happens is that everything remains the same, but you're differentiating with respect to x squared. It comes x squared e to the power minus alpha x squared dx. These two are not the same integration, of course. This is the differentiation with respect to alpha is what you get over here. Okay, so this x squared jumps out, but this is a variable. You have to integrate it with respect to that. All right. But if I go back and look at this one, this guy is that. So what I can do is, look at this. This is really interesting. What is this one here? This one here is d over d alpha. I already know that my answer is root pi over alpha. Where does that come from? Well, because this one, okay, this one I know is pi over alpha right here. This guy is root pi over alpha. So that's what I have up here, root pi over alpha. What you get here, well, this one would give you, if I sometimes actually wants to write it out in full form. So d over d alpha, I have pi over half, alpha to the power minus half, right? So when you bring it out, it would be 1 over 2. And then alpha would be 3 over 2, right? 3 over 2. And pi would be simply that, okay? This one I can write out as minus 1 over 2 alpha pi over alpha, okay? Pi over alpha. So look at this. This is just a technique. This integration now is equals to that integration, right? These two integrations are equal. So I can write now, because they have a minus and a minus here, I don't really have to worry about that minus. So I can say, so minus infinity to infinity x squared e to the power minus alpha x squared equals 1 over 2 alpha root pi over alpha. Okay, so that's great result. Just by differentiating, you can do this part. So this is something I need, but I can differentiate one more time. So just so that you remember we have minus alpha e to the power minus alpha x squared dx was simply root pi over alpha. And then this guy, if I have x squared, there's a 1 over 2 alpha comes in. If I differentiating one more time, so let me write this down. Differentiating again. differentiating again, what happens? Well, this guy, d over d alpha x squared e to the power minus alpha x squared dx. Again, I keep my x squared, I don't touch it actually, so it will become minus x to the power 4 e to the power minus alpha x squared dx, right? All right, but just like we did that part before, I know this guy is here, so what I want to do is I want to write but remember d over d alpha and 1 over 2 alpha root pi over alpha. What's that? Okay. This I can remember. Let me just redo this a little bit. This is half pi over half, and this was alpha minus 3 over 2, right? So let me erase this. I wish I had a bigger board. We should keep all this in mind. This is getting very confusing, right? But this is also exciting in some ways. That is, we're getting to know some new techniques that we can use. What do we have here? Well, you have minus 3 over 2. So when we take that, do this. This is pi. This is root pi, which is okay. All right. And then alpha minus 3 over 2 minus 1. Okay. What do I have? I have okay. I have minus 3 over 2 root pi, and this becomes alpha minus 5 over 2, right? So plus, because I'm bringing it down here. So minus 3 over 2. And then this I can, was there extra, sorry, I have a 2 here, right? I have a 2 here. So that 2 times 2 gives me 4. And this gives me 4. Give me 4 alpha squared pi over alpha. Okay, I have a negative there. But remember that what we're looking for is, so negative x to the power 4 e to the power minus alpha x squared dx equals to that. So so let's organize this thing one more time. So the first one was e to the power minus alpha x squared dx. That just gives you pi over alpha, right? So the second one is x squared e to the power minus alpha x squared dx. That gives you 1 over 2 alpha root pi over alpha. And the third one is x to the power 4 e to the power minus alpha x squared dx. And that gives you 3 over 4 alpha squared pi over alpha, right? Really interesting. So that's one. Then you have that's the third one, and then this is the second one, right? So these are the integrations that are going to help us in what we're going to do next, right? So what we're going to do next, we're going to, so keep this in mind, You have to refer to them. What we are after v square fv dv, and actually this is what we need to use actually. So I get a, because I have v square, it will be v to the power 4 e to the power minus mv square over 2kt dv. That's my Maxwell-Boltzmann distribution. I'm trying to figure out the average of that v square actually. All right, so we already know we are using alpha equals m over 2kt, right? M over 2kt. So this one would be equal to so remember, this is 0 to infinity, but we're using here negative infinity to positive infinity, right? So so what I need to do is I need to make this thing, so this is separate. So look what happens. I have to make this thing half. So what I'm doing here is that I'm going to go a over 2 negative infinity to positive infinity. Okay, I have x to the power 4 e to the power e to the power, so we have alpha minus alpha x square, because that's what alpha x square, and then we have dx. There's the same thing, x is v. The only reason I chose that is just to show you that we're doing the same integration. And now I have my result. What's my result? My result is simply I'm going to put this guy. This is my result right here. So what do I have? I have, let's say it gets a little bit complicated here right now. So let's hold our thoughts right there. So I have a over 2 3 4 alpha square pi over alpha. Right. Now I need to expand it and see what I get. I have all my, I know everything what a is. So let's go ahead, and what my a is 4 pi m over 2 pi kt 3 over 2, right? And then I got this. I have 2, and so there'll be 3 over 8. And what's my alpha square? Remember, alpha is this, so I can write it as m square, and on the top I can write kt square because it flips, and then pi to the power half, and then this alpha is m to the power half, and it goes to the top, 2 to the power half, kt to the power half. So you actually break it down like. All right, so let's finish up the root mean square velocity calculation. So what we have here was the integrand had x to the power 4, which was velocity to the power 4, you remember, and this is e to the power minus mv square over 2kt. So x and v are the same thing, so we have that expression. We already found out what that means. So this is what that is, right, with 3 over 4 alpha square root pi over alpha, where alpha is of course m over 2kt. So you write everything down, expand it. So that means put the value of a over here, and then what I do is that I organize all the pi's, organize all the numbers here, organize all the m's here, and kt's over there. Take a look at that. This is correct. And then what I have, all the pi's cancel out, and the numbers, the only 3 actually survives here, and the kt survives on the top and m survives on the bottom. So when you take basically the root mean square of that, so which is that, and then you end up with 3kt over m, and that's our answer. So that's your VRMS. So this is, we call it VRMS, V root mean square. So as you can see that we have most probable, which is 2kt over m, then we have in between 2 and 3, we have the average velocity, and this is the VRMS. All right, so here we are at the very last part of our velocity distribution calculations. So here we are looking at the entire distribution, and we are integrating from 0 to infinity. Basically, we are integrating over all velocities that's possible. So if you look at the distribution, basically it will fall, if you take any molecule, arbitrary molecule, and measure its velocity, it will fall under that curve. It will be somewhere there. So if you take the integration of the entire probability distribution, it will give you 1. So this one is our probability distribution. If you go from 0 to infinity, that should give you 1. So we are here, we're going to write this, we're taking half of it. Remember that all our exponential calculations were from minus infinity to plus infinity. So to go from 0 to infinity, you have to divide it by 2. And then over here, what you have is you get 1 over 4 alpha, because it used to be 1 over 2 alpha, root pi over alpha. And then you write this down. So alpha is m over 2 kt. So a is 4 pi, this entire mess right over here. And then you have over here is so this alpha over here, so it is 1 over alpha, so it flips, and then pi, root pi over here, and then 1 over root alpha, again it flips, so that's 2 kt goes upstairs and m is downstairs. Now you organize everything, so take all the pi's together, they all cancel out. Take all the numbers together, they will cancel out. Take all the m's together, cancel out, and they'll take all the kt together, that'll cancel out, and you'll end up getting 1. So the only thing that here, this is also the homework problem, this is how you do it. The only thing that you have to remember here is that is this integration right here. This integration that gives you 1 over 2 alpha root pi over alpha. That's the only thing you have to remember, and that's what you plug in. Okay? All right, so it's really a long calculation, and it's tedious a little bit also, but hopefully you will find it interesting, Thank you. I'll see you in class.